Welcome to today's deep dive. Whether you are prepping for a high-stakes robotics meeting, or maybe trying to catch up on the latest tech trends, or you're just insanely curious about where artificial intelligence is heading next, you are in the exact right place.
Yeah, definitely. There is a lot to cover today.
There really is.
Mm.
Today we're looking at a incredibly dense but absolutely groundbreaking technical paper. It's from a collaboration of researchers at Northwestern, Peking University, UC Berkeley, and Shanghai Tech.
Right. A huge joint effort.
Exactly. And it's titled MagicSim, a unified infrastructure for executable embodied interaction.
Which is, it's a massive piece of research. They are basically attempting to solve one of the most frustrating bottlenecks in modern tech right now.
Yeah, and so our mission today for this deep dive is to really understand how these scientists are building what is essentially the ultimate training matrix for robots.
The train matrix, yeah, that's a great way to put it.
Right. They are forcing artificial intelligence to interact with the physical world without cheating. And we're going to explore why this specific architecture is just a massive leap forward.
It really changes everything we know about simulation.
Okay, let's unpack this. To really understand the problem they're solving, think about the last time you played a video game, like a role-playing game, and your character needed to pick up a health potion.
Sure, yeah.
You walk your avatar up to the table, you press a button, and poof, the potion just magically teleports into your inventory.
Right, there's a little sound effect, and it's instantly in your pocket.
Exactly. You don't see the character actually reach out or, calculate the distance or adjust their grip strength based on the potion bottle's material.
Or lift the actual physical weight of it.
Right. The game engine just kind of edits the state of the digital world to make it happen.
And we accept that cheat because, well, it's a game. A hyper-realistic physics simulation of your character's knuckles just isn't necessary for entertainment.
But using that exact same video game logic to teach a real physical robot how to, say, make you a cup of coffee is an absolute disaster.
A complete disaster. Because suddenly, that magic teleportation trick is useless in the real world.
And that is exactly where the field has been stuck. Historically, in robot research, there has been this massive divide between the brain and the body.
Yeah, you essentially have two totally different camps of scientists working in silos.
It's like completely separate, right?
Completely. On one side, you have low-level robotics, and their focus is purely on physical mechanics.
So things like control, manipulation, torque limits.
Exactly, contact physics. They are trying to figure out how the motors in a robot arm can physically move a joint to grip a surface without the gears just snapping.
Which is hard enough on its own.
Very hard. But then, on the completely opposite end of the spectrum, you have high-level AI.
Right, the brains.
Yes. These are the vision language models, or VLMs, and they focus on reasoning, planning, and parsing human language.
So for you listening, the high-level AI is the part that hears me say, hey, clean up the kitchen, and breaks that massive abstract concept down into, step 1, locate the sponge, step 2, wipe the counter.
Exactly. But the fatal flaw in the industry has been that these two sides haven't really had a shared sandbox to practice in.
Because simulating real-world high-fidelity physics for millions of hours is just computationally exhausting, right?
It's massively expensive and slow.
Huh?
So to test those high-level vision language models quickly, researchers often test them in environments that rely on what the paper literally calls magic actions.
Magic actions.
Right. They use simulators that just force a task to be successful rather than simulating the mathematical, physical execution of it.
Wait, okay, I'm trying to picture this. So is this basically like a movie director yelling cut because an actor doesn't know how to pick up a prop?
Yeah, that's actually a really good way to think about it.
Right, so a stagehand runs onto the set, physically places the prop into the actor's hand, and then the director rolls the camera again. The audience sees the actor holding the object, but the actor never actually figured out how to pick it up.
What's fascinating here is that analogy perfectly highlights why older render pipelines are broken for robotics.
Because they're just faking it.
Exactly. Those older systems are forward-only rendering pipelines. They might generate a nice image sequence of a robot moving toward a cup and then suddenly holding the cup, but they throw away all the underlying interaction data.
Oh, wow.
Yeah, they don't mathematically track where the robot's fingers actually made contact.
Or like the friction.
Right, they don't measure the friction coefficient of the plastic or the required motor torque to overcome gravity.
So if you use the stagehand trick, you get a picture of a completed task, but That data is totally useless for teaching a real-world robot how to physically replicate it.
Exactly. The AI learns the sequence of events, but it develops zero physical intuition.
Because in your kitchen, there are no stagehands to magically teleport the sponge into the robot's hand.
No, sadly not.
If it doesn't know the physical difference between gripping a ceramic mug and a flimsy paper cup, it's just going to crush it or drop it.
Which happens a lot in early testing.
And this is why the MagicSim architecture is so critical. The researchers realized they had to force the high-level brain and the low-level mechanics into one shared reality.
They had to bridge that gap.
Right. The paper states that MagicSim is built around one deterministic batched runtime and a shared Markov decision process.
Yes, the shared Markov Decision Process, or MDP, is really the architectural commitment that makes everything else possible.
For the listener in me, when the paper says one MDP, 3 drivers, what does that actually mean in plain English?
Sure. In plain English, you can think of the MDP as the fundamental rules of the universe for a specific task.
Like the rules of the universe.
Yeah. It defines what the robot's cameras can observe, what physical actions its motors can take, how it gets rewarded, and what mathematically counts as a success. MagicSim defines this environment exactly once.
Okay, so one set of universal rules. But if I'm tracking this logically, the 3 drivers must be the different users or systems plugging into that universe.
Exactly.
So driver 1 would be a reinforcement learning algorithm, like the classic AI practicing by trial and error, just figuring out the physics over millions of repetitive attempts.
Right, the brute force approach.
And driver 2 is likely a scripted system, meaning a human engineer is hard-coding a perfect physical path just to collect high-quality trajectory data.
Spot on. And driver 3 is an interactive agent, like the vision language models we discussed earlier.
So a human types in a high-level language command, like pour the water.
And the AI agent has to figure out how to navigate that universe utilizing real simulated physics to achieve it.
That's incredible.
The real genius of MagicSim is that the physical task definition never changes.
Right, it's locked in.
Exactly. Whether a team is benchmarking an RL policy, or collecting scripted data, or interacting with a language model, they are all driving the exact same uncheatable physical simulation.
So you aren't building 3 different custom simulators for 3 different research teams. You're building one objective reality.
Exactly one.
There's an incredibly specific example in the paper, right, in Figure 1, that shows this in action.
Oh, the Unitree G1 sequence? Yeah, that's a standout.
It's crazy. It's a single continuous scene featuring a Unitree G1 humanoid robot. It walks across a room, crouches down to pick up a bottle, carries it to a table, picks up a teapot, pours simulated water from the teapot into a cup, places it on a tray, and then hands that entire tray to a seated human avatar.
It is a profound sequence, really, because of the sheer density of different physical interactions happening concurrently.
It sounds like it.
Yeah, I mean, you have bipedal navigation, whole body balance, rigid object manipulation, fluid dynamics, and human-facing interaction all at once.
And none of it uses the stagehand trick. It actually has to calculate its center of gravity to balance while crouching, and it actually has to simulate pouring liquid.
It's not faking a single frame of it.
But, defining the rules of the universe with an MDP doesn't mean anything if the universe itself is just made of cardboard.
True.
To make that teacup pouring example work, the robot can't just be interacting with solid, hollow polygons. We have to talk about how the engine calculates all of this, which leads into MagicSim's unified multi-physics backbone.
Right. A basic rigid body simulator, the kind you'd find in standard video games, is nowhere near enough for advanced robotics.
It's too simple.
Way too simple. MagicSim supports 15 distinct simulation families. In the paper, they refer to this as K = 15.
Okay, so 15 different physics types.
Yes. This includes articulated objects like cabinets with functional hinges. It includes finite element soft bodies, which behave mathematically like rubber or soft biological tissue. There are garments and cloth, particle-based fluids for the water, granular media like sand or rice, and even volumetric effects like fire.
Okay, here's where it gets really interesting. Because the paper makes a massive deal out of what it calls coupled multi-physics.
Yes, the coupling is the key.
They show visual evidence of an inflatable object hitting fluid and a rigid shovel digging into sand. And, as someone who has played video games with physics engines for years, this didn't immediately impress me.
Oh, really?
Yeah, because don't computers simulate a shovel hitting dirt all the time? Why is making sand and a solid shovel interact in the same simulation such a technical hurdle for robots?
Well, it comes down to the math. A rigid shovel in a basic simulation is calculated as one single geometric shape.
Okay.
The solver just calculates simple vectors for that one solid object. Sand, on the other hand, is a million body problem.
A million bodies.
Yeah.
Right, because every grain...
Exactly. The computer has to mathematically track thousands of individual tiny spheres, calculating the cascading friction and collision for every single grain, the exact millisecond the shovel impacts them.
That sounds like a nightmare for the CPU.
It is. Historically, if you put a rigid body solver and a granular particle solver into the same engine, the math conflicts.
What happens?
The physical boundaries intersect in ways the code just can't resolve, and the simulation either completely crashes or drops to a frame rate of like 1 calculation per minute.
Oh, wow. So previous research teams were totally walled off.
Yeah.
If they wanted a robot to practice shoveling, they had to build a highly specialized simulation just for sand, and that same robot couldn't then go practice pouring water.
Exactly. What MagicSim accomplishes is bringing all 15 of these entirely different mathematical families into one programmatic entity.
That's a huge breakthrough.
Huge. They can be instantiated in the same digital stage, advanced under one unified simulation clock, and observed together without crashing the system.
And how do they actually build that?
They achieve this massive integration through what the paper terms YAML first specifications.
Okay, let's translate that for you listening, because YAML is essentially just a configuration text file. It's a document that just lists settings.
Right, it's just code text.
Normally, if you put a 3D mug into a simulation, it's baked into the code as a heavy visual asset. The computer has to load all those polygons.
By using a YAML text file instead, I'm assuming the simulator doesn't have to load a bulky new 3D model every time you want to alter the scene.
That's exactly right. The computer just reads the text values, say mass is 2 kilograms, friction coefficient is 0.5, and procedurally generates the physical properties in real time.
So no huge rendering lag?
Nope. The visual and physical properties are bound together at the exact moment of instantiation.
Which means researchers can manipulate the environment at light speed. They can tell the system, load the simulation, but this time, make the mug 10 times heavier, make it completely frictionless, paint it neon green, and double its size. Just by tweaking a few lines of text.
Yeah.
And this creates what the industry calls domain randomization.
Domain randomization.
Right. By instantly randomizing mass, friction, color, and scale using just text, you feed the robot infinite training variety.
Ah, I see. So the AI doesn't just memorize how to pick up one specific red ceramic mug.
Precisely. It develops the generalized physical intuition required to pick up any cylindrical object regardless of its weight or surface texture.
But this brings up a glaring logistical issue in my mind.
What's that?
If researchers are using this YAML system to spawn thousands of these complex, randomized simulations with sand displacing, water flowing, humanoid robots balancing, and real-time friction calculations, all running simultaneously to train the AI,
Yeah.
how does the server not melt?
That is the exact question. Computational gridlock is the bottleneck that has plagued this specific field for years.
Because it's so much math.
When you force a high-level VLM brain to actually do the complex math of moving a physical body, the compute requirements skyrocket. But the researchers solved this through an architectural design called agent-level asynchrony.
Okay, the paper gets intensely mathematical here, but let's ground this in reality.
Good idea.
Imagine you're playing a massive multiplayer online game like World of Warcraft. The server clock ticks at the exact same speed for everyone in the world. The sun sets at the exact same time for every single player.
Right. That is what the paper refers to as the synchronized physics time.
But your individual character's actions are entirely asynchronous. You might be sitting safely in a menu screen, taking 5 minutes to decide what sword to equip, while another player is actively dodging fireballs in a dungeon.
Exactly.
MagicSim does this, but for thousands of robot brains simultaneously.
And if we connect this to the bigger picture, in older, perfectly synchronized setups, if you had a batch of 50 simulated robots and robot number 12 got its arm stuck navigating around a couch, it would suddenly need to calculate a massively complex motion plan to untangle itself.
Right.
Because the simulation was rigidly synchronized, the entire server would freeze.
So the other 49 robots would just stop mid-step, basically waiting for robot 12 to finish its math homework.
Yes. And that inefficiency made scaling impossible. So MagicSim introduces agent-level asynchrony inside a single batched simulator process.
So the physics don't stop.
Never. The physical world gravity, fluid dynamics, the trajectory of moving objects keeps ticking at a synchronized rate. But the semantic time, the heavy thinking of the agent, is asynchronous.
So how do they do the heavy thinking without lagging out?
To handle the intense path-finding math without pausing the universe, MagicSim uses an off-loop architecture powered by something called a Kurobo asynchronous microbatch solve farm.
A solve farm. Okay, let's think about this in the context of your daily life. Imagine you're walking through your living room and you see your dog sleeping on the rug in front of you.
Okay.
You don't have to pause time for everyone else in the house while your brain calculates the exact angle and muscle tension required to step over the dog.
That would be pretty weird.
Right. You process that pathfinding internally while the world just keeps spinning.
And that is exactly how the Kurobo solve farm operates. When a simulated robot needs to calculate inverse kinematics, which is the complex geometry of how to bend its shoulder, elbow, and wrist to reach a specific coordinate without colliding with an obstacle.
Right, trying not to hit the table.
Exactly. It doesn't force the main simulation loop to process that math. It delegates the calculation to a separate processor thread, the solve farm.
And while that separate processor is crunching the numbers, the robot just holds its pose or takes a safe default action. The physics world keeps ticking. The water keeps pouring in the other simulations.
Yes. Then, once the solve farm finishes the geometry, it returns the mathematical trajectory to the robot.
And the robot just consumes that result and executes the move seamlessly.
This simulator loop is never blocked by a single slow solve. It is a brilliant orchestration of computational resources.
It really is. Now, all of this staggering complexity, the 15 unified physics families, the YAML-driven infinite randomization, the time-bending asynchronous solve farms, it is all built to produce one singular output.
Data.
Exactly. It is an infrastructure designed purely to harvest golden data for artificial intelligence.
The entire pipeline flows from command to skill to planner to robot and finally to record.
So what does that recording actually look like?
When a humanoid robot successfully navigates a room and pours that cup of tea, the system is recording an incredibly rich, multi-dimensional spreadsheet.
Like everything is tracked.
Everything. It captures the RGBD camera footage, which is high-definition color video, perfectly synced with depth perception data.
Oh, wow.
Yeah, and it records the end effector waypoints, tracking the exact 3D coordinates of the robot's hands millimeter by millimeter over time.
That's insane.
It draws bounding boxes around target objects, and it precisely logs the human language commands that initiated the sequence.
It is basically the most detailed autopsy of a physical action ever constructed. But this is where I actually found myself questioning the paper's methodology a bit.
Oh, what caught your eye?
Well, the authors state that MagicSim acts as a success-gated filter. It specifically only saves what they call successful rollouts.
Right.
If the robot miscalculates its grip, shatters the teacup, and ruins the simulation, the system flushes the data and deletes it. But doesn't AI, just like humans, learn from failure?
You'd think so, yeah.
I mean, a human baby learns to walk by falling down 1,000 times. Throwing away the failure data just seems kind of counterintuitive.
That's a really valid point. In traditional low-level reinforcement learning, failure is absolutely required. The algorithm needs negative reward signals to map out what it shouldn't do.
Right, so why delete it here?
Because the end goal of MagicSim is different. The goal here is to train those high-level vision language models, the AI brains that translate English sentences into physical motion. To train them effectively using the current paradigms of behavioral cloning or imitation learning, you simply cannot feed them failure. They require a pristine data set of exclusively correct trajectories.
Oh, that makes sense if you think about it like teaching a child to spell.
Exactly.
If you give a child a book filled with typos so they can learn from the mistakes,
Yeah.
they will inevitably just memorize the typos as part of the language.
It's exactly like that. If you feed an AI brain a data set full of robots dropping cups and falling over, it might associate the concept of dropping with the command pour water.
Wow, it would perfectly mimic being clumsy.
That is the exact danger. MagicSim's success-gated filter guarantees that the agents are fed highly structured multimodal trajectories that flawlessly align the language command with successful physical execution.
So it's 100% accurate data?
Yes. When the AI processes the words pour the water, it is inextricably linked to the mathematical representation of a perfect pouring motion, complete with the necessary camera angles and joint torques.
You are effectively building an encyclopedic library of flawless physical intuition.
Which is exactly what's needed to move robotics forward.
So what does this all mean for you, the listener?
Hmm.
Why should you care about asynchronous microbatch, solve farms, and success-gated data pipelines?
It all comes down to the big picture.
It does. It comes down to this. MagicSim is the bridge across the biggest chasm in modern technology. Right now, society has AI that can talk. Chatbots can write essays, code software, and hold conversations.
But we severely lack AI that can actually do things.
Right. We don't have robots you can trust to safely navigate a messy, unpredictable living room and make your morning coffee without knocking over a lamp or burning the house down.
And that gap exists because the high-level planning and the low-level physical control haven't had a shared, computationally viable reality to practice in.
Until now. MagicSim provides that reality. It is the infrastructure where language finally meets actual physics,
It really is the missing link.
which leads to a final, slightly haunting thought from the end of the paper.
Oh, I know what you're going to bring up.
Deep in the capabilities list, the researchers casually mention that MagicSim includes animated human avatars for the robots to interact with.
Not just static mannequins?
No, animated digital humans moving through these simulated environments. We are now generating infinite, perfectly simulated worlds, complete with gravity, fluid dynamics, and friction, where robotic brains can practice serving items to digital humans millions of times a day.
The velocity of learning is about to become exponential.
Think about the implications of that. How long will it be until you interact with a physical robot in your own home? It gently hands you a mug of hot coffee, and you realize that its entire physical intuition was forged in a digital universe.
It's wild to think about.
Its knowledge of how heavy that mug is, how to avoid spilling it, and how to safely anticipate your reach. It learned all of that by serving a digital ghost millions of times before it ever met you.
It forces us to completely reevaluate what we consider experience and intuition. It remembers a simulated world far better than the real one.
The ultimate training matrix really isn't for us, it's for them. Thank you for joining us on this deep dive into the source material.
It's been a great discussion.
Keep questioning the world around you, whether it's made of real atoms or lines of YAML code, and as always, keep learning.